Okay, so it's really a tremendous, tremendous pleasure to be here, especially at the ICTP, which is a very special place to me. And I thank the organizers for inviting me to this meeting. So I'm going to talk about a subject that I've been working on for around 5 years. And that whole 5 years, I've had really one goal in mind, at least. Well, we'll talk about it a little bit more in the motivation part, but one very specific goal in mind, which, together with a number of collaborators, we were approaching more and more all the time. But if you had the misfortune to either read the conclusions of any of my papers or sit through any of my talks on the subject in this period, they always ended with some frustration that we were not quite there yet, that the goal was some totally new picture underlying the physics of scattering amplitudes, at least even very simple gauge theories in 4 dimensions. And while we were seeing lots of new structures and new objects, we couldn't cut the cord that connected us to the usual picture ultimately. So that was the complaint. And that situation has now changed. So in the last year, we now know at least one way of thinking about this physics, which is ab initio, starts from a completely different place. And at least so part 0 of this program that I started 5 years ago has been achieved, and that's what I want to tell you about. If I was braver, I would give a very unconventional talk where I wouldn't say anything about physics or gluons or n=4 super Yang-Mills. I would introduce a certain mathematical object to you that we call the Amplituhedron, and we just study it for a little while. I can explain what it is to a high school student. It's an incredibly simple object, and we'll talk about it. And then as we discovered it, as we start exploring it, we start noticing that it has all sorts of properties of things that we call scattering amplitudes for gluons, local evolutions through space-time, locality and unitarity emerging just as algebraic and geometric properties of this object. I'm not quite that brave, so I'll give a slightly more conventional talk, but that's really what this is about. Right? And I should say, so there's been a number of wonderful collaborators in this whole 5-year period. Some of whom are some of the sort of key pictures are shown in this are shown here. But what I'm talking about today is work that should a whole sequence of papers about it will come out in the next month or so with my former student, now off to Caltech, Yaroslav Tarenko. Okay, so oops, what happened here? Is that okay? Or, okay, I'll just leave it like this. Is it possible to have this single page? Okay, so very briefly on motivations, I'm going to talk about scattering amplitudes for gluons. But the real motivation has to do with some of the deep mysteries that we have to confront because of gravity and quantum mechanics. And we've all heard these slogans for a long time that space-time has got to be an emergent notion. And it's even conceivable that because of mysteries having to do with cosmology, that we have to understand quantum mechanics as emergent from some more primitive principles as well. The most obvious way of attacking those problems is to work on those problems directly. But there's another way that you can proceed that takes some inspiration from a previous epoch where we had to make similarly large transitions in our thinking. I mean, getting rid of space-time and seeing the quantum mechanics as emergent can't be a small thing. But we've done this before in physics. We went from classical to quantum, and there was a clue to quantum mechanics that didn't need experiments. It didn't need anything other than looking at the structure of classical physics itself, which is that in the way classical physics was given to us by Newton, it was manifestly deterministic as F=ma. But people discovered another way of thinking about classical physics in terms of the principle of least action, that when you first hear about it is very striking because doesn't seem deterministic. It seems like the particle sniffs out every path from A to B and picks the one that minimizes the action. Now, today we know why this second way of talking about classical physics exists. It bugged the people back then, why this totally different way of thinking about classical physics exists. But we now know why it exists, because the world is quantum mechanical. It's not deterministic, and the h-bar goes to 0 limit of the correct theory couldn't land you on Newton's laws, which is deterministic. It had to land you on a different way of talking about Newton's laws, where determinism isn't hardwired, but is seen as an emergent property. So people like Dirac and Feynman emphasize this a lot, that this is a path for progress always in theoretical physics, is to reformulate the physics you have right now under your feet in as many different ways as you can, because it's not necessarily obvious that the way that you first got it historically is the correct way to generalize to the next level. This is an old example, and I think it's conceivable that we're in basically the same situation today. We have to get rid of space-time and perhaps extend quantum mechanics. And one way of doing it is to try to reformulate good old-fashioned standard physics, quantum field theory, in a way where space-time and quantum mechanics don't play a starring role. Other principles playing a starring role, and you see the space-time, the local, and unitary evolution emerge. So that's the goal. So anyway, and of course before you find the principle of least action, then you deform it. There's finally a deformation that's not just reformulation into the path integral. But the first step is to find just the reformulation. Anyway, so the strategy is to reformulate all of quantum field theory, completely eviscerating locality and unitarity, and see them arise as emergent phenomena. That's step one. And step two, which would require more creativity, is to figure out what the natural deformation of this picture is in a way that removes the analog of discovering the path integral. Anyway, so this is the path that I set myself down around 6 years ago. Of course, we have to start with step one, and step one divides itself up into many steps. Step 0 of step one is to try to do this for the simplest possible non-trivial quantum field theory that we can attack, which is obviously going to be planar n equals 4 super Yang-Mills. Okay, so I just want to spend a few minutes telling you how locality and unitarity show up when you look at scattering amplitudes. So we're going to study the physics of scattering amplitudes. If someone hands you a bunch of scattering amplitudes, they didn't tell you how you computed them, how would you know that the result is local and unitary? Now, obviously, locality and unitarity are hardwired into the usual way of doing quantum field theory. That's the whole point of Feynman diagrams. That's why Feynman became famous, is because Feynman diagrams allow locality and unitarity to be manifest step by step in the construction of the amplitudes. And Feynman diagrams also make it obvious that as a consequence of locality, let's say I'm looking at tree amplitudes, summing over all trees, locality tells you something about where the poles of the amplitude are. That the only poles occur when a sum of the subset of the momenta of the particles goes on shell. Okay? That's non-trivial. If I hand you a random function of momenta, it's not obvious that all their poles will look like that. Okay? But all the poles have got to look like that. That's locality. And at tree level, unitarity is the statement of what happens near those poles. That on those poles, the amplitude has got to factorize into trees on the left times trees on the right. Okay? So that's a statement at tree level. At loop level, locality and unitarity, well, in textbooks, they have something to do with the optical theorem, discontinuities across branch cuts, and so on. But they have a simpler avatar in the cut structure of the integrand for scattering amplitudes. For example, if you look at the famous unitarity cut of some one-loop amplitude or some L-loop amplitude, it's got to break up into gluing together two lower point loop amplitudes integrating over the on-shell phase space of these two intermediate particles. So someone has to then tell you that they give you this the formula for the integrand. You have to see the integrand has singularities where internal lines go on shell, and in the neighborhood of those singularities, again, it has to factorize in a certain way. In planar theories that have enough supersymmetry, you can go further. There's a sharp notion of the integrand for the loop amplitudes. And locality and unitarity, locality is a statement of where the poles are, and unitarity tells you how it factorizes on the poles. And there are two kinds of singularities that you can have in the integrand. A factorization piece and what's called the forward limit, or a single cut, of the amplitude, which is determined by the forward limit of the one lower loop amplitude with these two particles having equal and opposite momenta. So if someone hands you an integrand and says, I got it, this is how you check to see if they're lying. Okay? If it satisfies this, then it's local and it's unitary. And Feynman diagrams make this obvious. That's their job in life, is to make this fact obvious. In fact, if someone told you, I have some new whiz-bang way of getting functions that satisfy that these are the singularities, you'd wonder, how the heck are they doing it, right? Because obviously the only way to get this singularity is if there's some gluon going on shell in there, for example. Where are you getting it if you're not talking about things evolving in space-time and so on? Well, that's what we're going to see. We're going to see a totally different structure today, which gives rise to exactly the same equation, despite the fact that there's no Hilbert space, no gauge symmetry, no path integral, no space-time, no quantum mechanics. All right. Now a little bit more on some of the variables. Just two quick things about kinematics. Scattering amplitudes are functions of helicity and momenta. We're going to do things maximally supersymmetrically, so all the helicities are unified into a supermultiplet, and they're labeled by a Grassmann parameter. And on top of that, we use these spinor helicity variables to describe the external momenta. And we do even something extra beyond that. There's an even nicer way of talking about the external data that takes advantage of a twistor representation. Very simple algebraic change of variables from usual spinor helicity variables to new variables. But all you need to know is that the four variables for the momenta of the particles are translated into four new variables, which are just points, just four-dimensional vectors up to a rescaling. So they're points that live in a three-dimensional projective space. Given that data, you can build external massless momenta which conserve momentum. Okay, that's the first thing. And the second quick thing is by this correspondence, if we want to think about what the loop integrand is, instead of thinking about the loop integral in the usual way, like labeling that line to have momentum L, when we draw these diagrams, we instead look at a dual diagram. Integrating over that momentum L is the same as integrating over the position x of the dual coordinate. And this position x, further under this twistor map, maps to a line in the same three-dimensional projective space. So the scattering amplitude, very concretely, you pull out some momentum conservation, essentially. And the thing which is left is a function of these external points that live in three-dimensional projective space, and at L loops, it's a function of L lines. And it has to have very prescribed singularity properties in order for it to be local and unitary. Now, as I said, Feynman diagrams make it obvious that this is a singularity structure. And they also make the conformal symmetry manifest in n equals 4 super Yang-Mills. One of the remarkable things that people discovered 6 years ago, and we've learned more and more about sharply, is that there's a totally different picture that gives you exactly the same formula and exactly the same property, where instead of calling it a scattering amplitude, you think of it as an expectation value of a Wilson loop, whose corners are exactly the first line is the momentum P1, P2, P3, and so on. Okay? So this is very remarkable that there are two objects, one that lives in one space, the other one that lives in a dual space, that calculate exactly the same thing. They have exactly the same singularity structure. So this is already a hint that there's, obviously, it's got to be another way of talking about the physics, where not one space-time or the other space-time are manifest, but it doesn't depend on either one of the space-times. So this makes the dual conformal symmetry manifest. This symmetry and that symmetry commute to an infinite dimensional symmetry known as the Yangian. And this Yangian is impossible to see in any one of these two descriptions because they pay too much attention to space-time, either one or the other. But it should already awaken you to the fact that there is another way of generating exactly the same kinds of singularities. Instead of saying there's some gluon going on shell, you can say that, oh, the reason there is a singularity is that I have this null Wilson loop, and two of the points are becoming null separated from each other. And that gives me another way of getting a singularity. Okay? So what we've been after for a long time is just what I said, is a third way of thinking about the physics, which doesn't depend on one space-time or the other. It doesn't care about space-time at all. Also, somehow, this emerges. So locality and unitarity are not hardwired, but are emergent. But, for example, amongst other things, the infinite symmetries should be manifest, and other things should be manifest as well. Okay. Now, one thing along this path, which we talked about in a paper back in a long paper back in December, is the realization that scattering amplitudes can actually be represented in a completely on-shell way using these so-called on-shell diagrams. So you draw pictures like this. These aren't Feynman diagrams. These are the elementary three-particle amplitudes of the theory, and every particle that appears here is totally on-shell. Even the internal lines are totally on-shell. We just integrate over their phase space. So these things are called on-shell diagrams. Remarkably, it turns out that amplitudes can actually be represented in terms of these on-shell processes, despite the fact that we normally think of them as involving virtual particles. But in this picture, there's no virtual particles. That's the four-particle tree amplitude. That's the four-particle one-loop amplitude represented in terms of these on-shell diagrams. And so that's the physics idea, is that you can compute amplitudes using directly as on-shell processes. But this turned out to be related to a remarkable mathematical object that mathematicians themselves had run into in the past 4 or 5 years, roughly simultaneously with when we ran into it as physicists. Okay? And that's why we had some fun talking to them, realizing that we had been seeing exactly the same beast. The mathematical object has to do with the so-called positive Grassmannian. So let me just tell you in a microsecond what the Grassmannian is. The Grassmannian can be thought of as the space of k-dimensional planes in n dimensions, but you can also think about it concretely as a k by n matrix where you can do any k by k linear transformation on it that you like. So it's modded out by GLK. Think of the columns of this matrix as just n k-dimensional vectors, C1 through Cn. And so that's the Grassmannian. The positive Grassmannian puts a constraint, says all these things are real, and puts a constraint that if you take any k by k minor of this k by n matrix, that it's positive. Right? One simple additional thing, that all the minors are positive. And that puts a world of structure on this object. And just to give you a picture for what positivity means, let's say I'm doing it in G3n. So I can think of each one of the columns as a three-dimensional vector. Since I can rescale them by constant, I can really think of them as points in a two-dimensional projective space, or just points in Euclidean space. And you can ask, what do the points have to look like in order for the matrix to be positive? And the answer is that those dots have got to make a convex polygon. Okay, so if it's a convex polygon, then the corresponding matrix is positive. Anyway, there's a whole story here that I don't have time to review, but these things, the two things I told you about are not obviously related, and yet they're actually intimately related to each other. These pictures of space-time on-shell processes are in one-to-one correspondence with up to a certain set of equivalencies, physical equivalencies, are in one-to-one correspondence with so-called cells of this positive Grassmannian, which in turn are in one-to-one correspondence with a new way of thinking about permutations. Okay? So there's an essentially combinatorial thing underneath all of this, which is a new way of thinking about permutations. And so you give me a certain permutation. Given the permutation, there's a graph associated with it. There's a cell in the positive Grassmannian associated with it. To find the permutation associated with the graph, you walk into the diagram, you make a right turn where there's a black vertex, you make a left turn where there's a white vertex, or crazy things like that. And yet, this is all about physics. In fact, this underlies all of scattering amplitudes for n equals 4 super Yang-Mills. So that was the status as of December. Oh, and also, this infinite symmetry is totally obvious in this picture. It's just positive diffeomorphisms that keep you inside this positive Grassmannian. So indeed, everything is obvious. Okay? But this was a beautiful story for building blocks of the amplitude, but not yet a beautiful story for the full amplitude. The thing that dictates how we combine these on-shell processes together to get the actual amplitude. See, we have individual pieces, or these on-shell processes, but we have to add them together in a specific way to get the full amplitude. One way is by using the extension of the BCFW recursion relations to loop-level processes. That's one way of doing it. But you can ask, why are we gluing them together in this way at all? Why isn't the answer just one of them? Or why do we have to take them and add them in these certain funny combinations? And the answer is to make the result local and unitary. Okay, so that was the complaint. That's what was bugging me. I wanted to see locality and unitarity emerge. That was the whole point. And we're getting closer and closer to it. We're seeing these very new building blocks to build the amplitude out of. But ultimately, even though the building blocks have this beautiful story associated with them, we didn't know why we were gluing them together in this particular way to get the answer. There's zillions of ways of gluing them together, all of which gives you the same answer. But why are we gluing them together in that way? Anyway, we have to go through this in detail. The very simplest example of this happens already for the first non-trivial tree amplitudes, where there's a single object, a single kind of on-shell diagram. It's associated with the Grassmannian in a certain way. You don't need to pay any attention. But all you need to know that it's labeled by sort of 5 labels like this. And what you're instructed to do by the BCFW recursion relations is add up this particular combination of them. And it's weird. You know, like it has some structure. It's not manifestly cyclically invariant, for example, even though it turns out to be. But why? Why are you adding these guys up? Okay? Why not add up another combination? Okay. And around 2 years ago, there was a vague fantasy that began with a very beautiful paper by Hodges that we followed up with him, which was sharp in a very simple case, but it wasn't obvious how to extend. The vague fantasy, because it's vague, I can say it vaguely, is that the amplitude is really the volume of something. It's the volume of some region in some space. And if you want to compute it, you have to triangulate this region. There's lots of different ways of triangulating it. It'll give you the same answer. And that if we figured out what this space was and what this volume was, we could also understand how locality and unitarity emerge. Okay, so that was something that we had been trying to do for 2 years, and that's what we now know how to do exactly. Okay? Now, as I mentioned, we ran into this object known as the positive Grassmannian, which the mathematicians had run into roughly simultaneously from, of course, completely different points of view. So that was exciting and a lot of fun. But this object is unknown to the mathematicians. Okay, so that's also gratifying because the full amplitude knows more. It knows way more than the mathematicians knew before. Okay? And not just the mathematicians knew about the building blocks, the full amplitude knows about an object that they did not suspect existed. In fact, many of them were very surprised that it can even exist. Okay? And so we have to give it a name because it doesn't have a name, so we called it the Amplituhedron because it combines the two obvious features. It's coming from thinking about scattering amplitudes, and you think of it as this beautiful, enormous polytope that lives in an infinite dimensional space. Okay? So the rest of the talk, I'm going to tell you about the Amplituhedron. And the good news is that the Amplituhedron is the generalization of an extremely simple idea. As I said, I could have skipped the whole first part of the talk, which is physics motivated, started at this point, and as you see, this can be explained to a smart junior high school student. We'll start with triangles. So draw a triangle on a plane. And let's say I want to talk about the points on the inside of that triangle. The points on the inside of the triangle, you can think of the corners of the triangle of having masses C1, C2, and C3. So the points inside the triangle, if they had masses C1, C2, and C3, the center of mass is in the triangle. So varying over all the masses, you cover the inside of the triangle. Right? So this is more nicely said using projective coordinates that the points on the inside of the triangle are the form C1, Z1 plus C2, Z2 plus C3, Z3, where the C's are positive numbers. And since I can rescale the C's and get the same point, they're positive numbers modulo GL1. Now, this notion of the inside of a triangle generalizes to the inside of a simplex in a higher dimensional space. And further generalizes if you take these from being just numbers, which are one-dimensional vectors, to k-dimensional vectors, then this triangle, which generalizes to the simplex, this generalizes to the positive Grassmannian. That's just what we talked about a second ago. Okay, the k-by-n matrix with all positive minors. So the positive Grassmannian is the generalization of the notion of triangle. Okay, so the entire previous subject is about the generalization of the notion of triangle into the Grassmannian. There's another obvious generalization, which is to talk about polygons instead of triangles. Right? So now let's say I don't have 3 vertices, but I have n vertices, and I want to talk about the inside of a polygon. You have an immediate problem. What do you mean by the inside? If I hand you a bunch of vertices and they're randomly distributed, there is no well-defined inside. Okay? The only way there is a well-defined inside, where these guys are the vertices of the object, is if the polygon is convex. So first, you've got to make sure that the external data is nice. The external data have got to make the polygon convex. I just told you a little while ago that making the polygon convex is the same as saying that the external data is in the positive Grassmannian. Okay? So the external data is positive. And to find the points on the inside of the polygon, you have to combine them, again, with positive coefficients, the same center of mass idea. So you see, we have something a little interesting. The inside of a polygon is jamming together 2 notions of positivity. First, the external data is positive, and secondly, they're being combined with positive internal data. And this idea generalizes in a number of ways. So this is the formula. Y is equal to CZ. And of course, specific choices of the C's, specific cells of this, of that simple little Grassmannian for the C's are just the triangles in this picture. And you can also triangulate nicely, not just cover them randomly, but triangulate in a nice way. And here is the simple triangulation. Okay? There's also a natural notion of the area of the polygon. And here I'm going to have to skip over a little bit. There's the intuitive notion of an area, but there's a dual notion to an area, which is a little more subtle. In this case, they're literally Poincare dual to each other. You can also, instead of thinking about the area, you can think of a certain two-form that lives in this two-dimensional space. And this two-form has the property that it has singularities on the corners of the triangle or of the polygon. Singularities of a certain specified sort, so-called logarithmic singularities. So it looks like dx over x as you approach any of its boundaries. So you can either talk about the area of a polygon, or equivalently, you can talk about a certain two-form, omega. Given any region P, you can talk about a certain two-form which has logarithmic singularities on the boundary of that region. And if you want to figure out what it is, one very simple way is to triangulate. If you're handed a triangulation, that immediately tells you what that two-form is, because the form for each one of the triangles is trivial. All right, so this is just thinking about polygons. And now we're just going to generalize polygons into the Grassmannian. Generalizing polygons is going to give us scattering amplitudes. The first generalization is to go to exactly the same formula and just say that those are higher dimensional vectors. Okay? Not just the two-dimensional points in two-dimensional space, but in a higher dimensional space. Everything is exactly the same. The external data is positive, the internal data is positive. For good reasons, these have to be even dimensional vectors. So the polygon was the case m equals 2. The first new case is m equals 4. This is harder to visualize, but you can get the hang of it pretty quickly. And remarkably, you find when you triangulate that object, that one triangulation is a sum over the following set of four-dimensional simplices. 1 ii plus 1, jj plus 1. Now, I don't know if you remember from 10 slides ago, but there was a formula for the scattering amplitude, which looked exactly like that. The sum of 1 ii plus 1, jj plus 1. And I said, why the hell are we adding these objects together in that way? We didn't know why we were adding them up in that way before. Now we know. They're actually triangulating the amplituhedron. This is our first example of the amplituhedron. Okay? And in fact, these simplest tree amplitudes, non-trivial tree amplitudes, are literally the volume of this object, in the sense that I said before. The four-dimensional object is hard to visualize. I can show you what one of its three-dimensional faces looks like. Here's one of its three-dimensional faces, for the case of 8 particles. And the volume of this guy literally computes this helicity amplitude. Okay? So of course, other helicity amplitudes you get from the full four-dimensional object. It just so turns out that this particular three-dimensional face corresponds to that particular physical process. You give me the external momenta of the gluons. That just tells me where to draw these points. I draw this amplituhedron. I compute the volume. That's the amplitude. That's hundreds of pages of Feynman diagrams. And it's not just that the answer is simple. We've known for a while now that the answer is simple. The remarkable new thing we know is we know a different question that the amplitudes are the answer to. Okay? There's no local evolution through space-time. There's no S-matrix. There's none of that. There's this geometric object and its volume. And the amazing thing is that this geometric object and its volume has all the properties of scattering amplitudes. Okay? And in fact, this gives you the way of thinking about scattering amplitudes where all of its properties are manifest. Anyway, let me now go through the rest of it very rapidly. This generalizes. Instead of just having one point y, we can have k points y, and look at the k-plane, which is made out of those k points. And it's exactly the same thing. It's always a formula, y equals cz, where both of these guys are positive. Now this is in the positive Grassmannian in the sense of gkn, and the external data is again positive. Okay? One thing that, this is just a small comment since it's a SUSY conference, everything here is supersymmetric, and we've been very used in this business to be talking about superamplitudes. So the variables are naturally supersymmetric. There are 4 bosonic and 4 fermionic variables, and the geometry is supergeometry, which is what we're used to. It lives in a projective space, superprojective space, P3/4. One aspect of this whole story I don't have time to describe in detail is that there's a new way of doing supersymmetry, not superspace. A totally new way of doing supersymmetry, which is much more bosonic. Much, much more bosonic. And instead of talking about points in P3/4, we talk about bosonic objects in P3 plus k. And this allows us to replace supergeometry by bosonic geometry. And there's a very specific rule for how to do it. Now, once you know all of that, you have this region, y equals c dot z. That's it. That's the whole object. The volume of that region is the tree amplitude. Done. Okay. And the BCFW recursion relations give us one way of triangulating these objects, but there are many others. simple geometric properties of the amplituhedron encode locality and unitarity. Okay? So just from the definition as given, just from that y equals c dot z, nothing else, you first of all learn that the boundaries of this beast are interesting. There are very specific sorts of boundaries. Very specific planes made out of the external data give you the sort of first faces of this object. The specific faces are exactly the ones that tell you that the poles are local. Part of this whole dictionary I don't have time to explain is that the singularities of the amplitude correspond to boundaries of this object. Okay, so you want to find singularities, you move to the boundaries. So the kinds of boundaries that the amplituhedron has tell you where the singularities are, and that's where locality is. And locality is a consequence of that. Unitarity tells you that as you approach a boundary, the amplitude has got to split. And that's beautifully reflected in the positive geometry. Literally, as you approach the boundary of the amplituhedron, on the boundary you see that it breaks up into lower amplituhedrons that are glued together in exactly the way that amplitudes are supposed to be. There's no gluons propagating in space-time. There is no space-time picture of any sort. This is, again, just a simple consequence of positivity. So that's a story for tree amplitudes. What about loops? Well, here too, I don't have time to motivate it, but the guiding principle is you have this huge amplituhedron in principle for any number of particles, infinite number of particles. What if you wanted to ignore a bunch of them and just look at a finite number? Literally ignore them, hide them. You want to hide particles. Okay? Hiding particles means something very specific in this geometry. It means projecting away from certain points in the underlying geometry. And it turns out that there's an essentially unique way of doing that mathematically makes any sense. That unique way picks out, remember I told you that the loop variables are lines in this projective space. So first of all, it tells you that anything you're doing can only be done with lines. It can't be done with points, for example. It has to be done with lines. And secondly, it tells you something about these lines themselves living in a certain positive space of exactly the same structure. Okay? So those lines have got to be given in terms of positive combination of the positive external data that satisfy a positivity constraint that if you now take these 2-by-n matrices, these turn out to be 2-by-n matrices, stack them all together, all the minors of this matrix are positive. And as I said, that actually arises from thinking in terms of hiding underlying particles. Just so you see how concrete this is the simplest case for 4 external particles. Okay? This is just for the 4-particle amplitude to any loop order. Computing the 4-particle amplitude to any loop order, so any loop should have 4 variables. In this twistorial representation, those 4 variables are right here. X, Y, Z, and W. Okay, so there's 4 variables there. The 4 variables are the L0, L1, L2, L3. That's the usual variables. This is the 4 other variables closely related. Well, you group them together in 2 sets of 2-dimensional vectors. So A's and B's. And they have to have the property that all the components are positive. So these are just points that live in a 2-dimensional space in this upper quadrant. Right? So that's one constraint. The other constraint is that if you take any pair of them, AI minus AJ, dot BI minus BJ should be negative. That just says that if you take the line from A1 to A2 and the line from B1 to B2, that they always have to be going in opposite directions from each other. That's it. You now have to study that space. Study that space means understand that space. Put coordinates on that space. Triangulate that space. Triangulate that space, we're done. We've computed the 4-particle amplitude to all loop orders. Okay, so this is the problem that we can give to a junior high school student. Well, Yaroslav and I have been struggling to solve this junior high school student problem for about 4 months now. So, but it could well be that there's, it's one of these things. It could well be someone could just have a brilliant insight and just write down the answer. Even without writing down the answer, it's remarkable, just like we saw before at tree level, that simple geometric identities that follow from positivity that I don't have time to explain tell you that the singularities going to certain boundaries of this object break it up into pieces like that. So here's unitarity, textbook unitarity, once again, as a consequence of positivity. Textbook unitarity is some property of this little geometry problem with points moving along with these constraints that any pair of them are obtuse relative to each other. And because this is such a simple to say problem, we think that it's at least in sight to do something for the first time, which is completely solve for the integrand of a quantum field theory in 4 dimensions, all loop orders. This is something we've implicitly done using recursion relations, and other aspects of the problem have been implicitly done. The entire amplitude, when you integrate two, at least logarithmically divergent pieces of them have also been computed to all loop orders using techniques from integrability and so on. But the full integrand has a huge amount of extra information, and that's something that no one has done before. Okay? In principle, you can do it recursively, but that doesn't mean that you can write down closed form expressions. And so we feel it's conceivable that we can actually do this. Right? Now, what we've been doing for a while is trying to understand just this amplituhedron in this four-dimensional case by understanding its faces. So like someone hands you a big complicated polyhedron, maybe you want to see what the faces look like first. Thinking about the faces corresponds to computing cuts of the amplitude. And that we've done already. That's what we spent a number of months doing. And we've calculated many, many infinite classes of cuts to all loop orders. These are already information about the integrand to all loop orders that is the first time we have such information. And I can tell you, you can do it, on a piece of paper, and once you get the hang of doing these things. And you can then check. Again, so you're predicting things at all loop orders. The integrand is known to 6 loops, so you can check up to 6 loops whether your predictions agree with experiment. In this case, experiment is the people who've done the computations. And just to show you that there is meat in this business, on the flight over here, just as one of the things that I was doing in preparation for our papers, I computed one of these infinite classes. It's one, I don't need to describe what this is in detail, but we have these L1, L2, L3, L4 lines, and they're in this particular geometric configuration where a bunch go through these corners, and the other ones line certain planes. That turns out to correspond to certain cuts. And on the plane, I found the analytic result. It fits on half a page. I didn't write it down because it uses some notation that I would have to explain. But it writes, I could compute it on a flight while being interrupted constantly and suffering from lack of oxygen at 30,000 feet, okay? But then you just, it's a finite expression, very simple to write down expression, but it involves summing over permutations of labels and so on. So I gave it to Mathematica, and that's what it looks like. And then I got bored. There's sort of 6 more pages where that comes from. And then you compare it to the answer. Of course, it works exactly. Right? So you really get the feeling that you're doing things in a different way when we're not drawing recursion, there's no diagrams, period. Right? We're just manipulating these little geometry problems, and the fact that at the end of the day you've computed some very non-trivial thing about the scattering amplitudes really gives you a feeling that you're doing things in a new way. Anyway, so let me just end by defining the amplituhedron in general. So this is it. This is the mathematical object. Okay? This is the amplituhedron it depends on n, k, and l. N is the number of particles. K is the k of n to the k mhv amplitudes, and L is the loop order. And the space is the space of k planes in k plus 4 dimensions. That's what this y space is. It's k planes in k plus 4 dimensions. So that y equals c dot z story was just about tree amplitude. So that was just about that k plane. But then you would see there's something missing still that you could be doing with the structure, because orthogonal to that k-plane in k plus 4 dimensions is a nice 4-dimensional space, which is empty at tree level. And all loops are doing is populating that 4-dimensional space that's dual to the k-planes with L lines. So that's the space. The space is k-planes in k plus 4 dimensions with L lines in its 4-dimensional dual. And then it's a part of that space, the analog of the inside of a polygon. It's a part of that space which can be written as a positive combination of positive external data. That's it. That's the amplituhedron. The volume of the amplituhedron is the L-loop scattering amplitude. Okay? And as I mentioned, the ideas are extremely simple. They just generalize the notion of a triangle, which generalizes to the positive Grassmannian, and the polygon itself that generalizes to the amplituhedron, together with the idea of hiding particles as the origin of quantum loop corrections. And this feature, locality and unitarity, are a consequence of positivity. And you can see that they're a consequence of positivity. They're not as trivial as with Feynman diagrams. You have to explore a little bit. But you don't have to finish solving the whole theory and then realize that it's local and unitary. It's a feature of the geometry that makes it obvious that it's local and unitary once you know how the geometry works. All right. All the symmetries are manifest in this picture. And determining the integrand is just reduced to a question of triangulating this region. Okay, so that's the work that we've been doing for a while now. I mean, we've known this basic structure since late in February, and what we've been doing since is just learning enough about how to triangulate it so we have something reasonable to present as far as having some understanding of what it is. And perhaps, as I hope it was clear, the object is extraordinarily simple, but it's not known to the mathematicians. Okay? So unfortunately, they can't just... In our previous story, we were groping around and seeing some structure in the Grassmannian. We had these pictures with black and white vertices. Then we realized that mathematicians were talking about vaguely similar things, and we started talking to them. And to our amazement, they had invented exactly the same pictures with black and white vertices, and they're doing exactly the same things. There's a lot of familiarity, so that was wonderful. And we could learn a lot from the mathematical things about it that they had already explored. But this is a case where the physics is now well ahead of both the physicists, obviously, and the mathematicians, perhaps even more obviously. But I think it's going to be a lot of fun to try to work out what it is. But anyway, as I said, it's a very simple mathematical structure that gives a complete and autonomous definition of all scattering amplitudes in this admittedly very simple theory, planar n equals 4 super Yang-Mills, which finally is totally free of the usual quantum field theory language. Okay? This is the thing that was missing before, as I said in the beginning. But finally, I can start ab initio and talk about polygons and triangles and polygons, and there's no Feynman diagrams, obviously, no path integrals, no gauge symmetries, but there's not even on-shell diagrams, no recursion relations. It's an object that obviously exists on its own, and we can see the rest of it emerge. Just twistor space played a very important role in setting up the good kinematic variables of the story, but it didn't have any dynamical content. Of course, it doesn't have dynamical content. What gives you, the remarkable thing is what gives you dynamics is just one extra idea, this idea of positivity. And that's it. So you're in the correct space, and you think about this positive structure, and you're done. And so to conclude, I think we can say that we now have a first, admittedly very baby example of what emergent locality and unitarity, emergent space-time and quantum mechanics can actually look like. The structure, as I said, is as of yet unknown to mathematicians. Not only is it unknown, they're surprised that it can exist. I don't have time to explain why, but they're surprised that it can exist. And it generalizes by quite a lot the idea of the positive Grassmannian itself. So we're going to have some, we have a lot of work ahead of us to understand what this thing is trying to tell us. But let me just end with some general comments and speculations. First of all, this entire subject is an example of doing physics, this kind of thinking about this type of thing beyond the idea of dualities. Dualities were a very, very big deal. They have very profoundly impacted the way we think about all of physics, certainly more formal aspects, even lots of applications all over the place. Dualities are incredible things, but dualities do not involve dualities involve making connections between existing things. So there's gauge theories, two gauge theories. We knew them both beforehand. We know what gauge theories are. We know that formulation. Each formulation has its own sets of gauge redundancies. Then the remarkable thing is that two different sets of gauge redundancies describe exactly the same physics. It's an amazing thing. Amazing thing that gauge theories and gravity are the same. But again, it's two things where we had the words and the language ahead of time. They seemed naively different, and we found out that they're actually the same, right? We've gone a long way with that, but I think it's clear that we have to do something beyond that even. We can't just keep making equivalences between essentially ideas that were handed to us from the early part of the 20th century. We have to find really new things, okay? Really new things as well. This is an example of a really new thing. Okay? This is not standard gauge theory. It's obviously not gravity, but it doesn't have any of those normal variables or language or anything. Of course, the fact that it's another way of talking about exactly the same thing is evocative, right? That there may be yet more ways of thinking about it, and I think we need to find what these ways are, understand more deeply why they exist, where they're coming from, and I suspect that's going to tell us something important as we head towards really trying to come up with what the idea of emergent space-time might mean in general, not just for these very toy theories. I've talked about planar n equals 4 super Yang-Mills. I don't have time to go through this in detail, but anyone who's interested, I can tell you the circumstantial reasons I think there must be similar structure for gravity, and even more importantly, similar structures for perturbative string amplitudes. And maybe I'll just end with this, that a slogan that many of you have heard has been said many times is that space-time has got to be emergent for all the usual reasons having to do with gravity and quantum mechanics. But if you think a little more about it, I think it's very unlikely that just space-time is emergent. And that if space-time, including the time part, is emergent, and that's the tough part, then it seems very unlikely to me that quantum mechanics is just going to sit there with space-time being emergent. I think space-time and quantum mechanics have to emerge hand in hand for some more primitive principles. That's what I suspect is going to be true in general. That's definitely what happens in our baby n equals 4 example. Okay? In this example, there is one idea of positivity. That one idea gives rise to locality, and it gives rise to unitarity. There's nothing I can do to that picture that would just make it classical without there's no way I can remove those two. There's no way I can remove that link. Okay? Once I say the one underlying principle, it's simultaneously local and unitary. And of course, it's fascinating because in the usual way of doing quantum field theory, it's exactly the other way around. Locality and unitarity fight each other. That's why we have to introduce fields and redundancies and all the rest of it in our usual way of doing field theory in order to make relativity and quantum mechanics play nicely. In this picture, there is no space-time, there is no quantum mechanics. There is something else, and they emerge hand in hand. Again, this isn't a very baby, very simple example, but it's something I suspect is going to be, or I hope is going to be true more generally. So maybe I'll end it with that. I have a wild fantasy on my last slide, but that will stretch Eric's patience with me even more than it has so far. So thanks a lot. Not so bad, not so bad.
Thank you, Nima, for this inspiring talk. We have time for questions. Over there.
I have a naive question. You know, with this fair and fast war going on, it seems like people are questioning the locality and the unitarity of quantum mechanics. But you seem like saying you still believe those two are like essence of quantum mechanics.
Well, that's what I was saying in the very first part of my very first slide, is that certainly, well, if we have asymptotically flat space-time, so we're talking about a question like the S matrix, even including black hole formation and evaporation, there's no reason to question quantum mechanics at all. When I said quantum mechanics might need extension, it's for very subtle things involving cosmology, maybe inflation, or the accelerating universe, things like that. If you have a question involving black hole formation and evaporation, there's no reason to expect anything quantum mechanics even needs extension. Okay? Locality, on the other hand, is almost certainly not there, fundamentally. Okay? So that's all the usual reasons. And so, indeed, that's not a new thing. People have been saying that for ages, that somehow space-time has got to emerge from more primitive ingredients. Holography in the ADS-CFT correspondence is a step in that direction, but time isn't emergent in that case. But anyway, so that is all great. So what I'm suggesting is that ultimately we have to get rid of locality, precise locality. Gravity makes precise locality impossible, and ultimately, probably because of these cosmological questions, quantum mechanics may need some extension. Okay? What I'm suggesting is a way to get there, and the way to get there is not to try to guess at the right answer, or to swim around in literally these questions. Okay? That's one way to get there, is to try to think very hard about black holes and how the information comes out, and singularities and eternal inflation. Those are the kinds of questions where these issues hit you at order 1, right? So you could do that, and that's what a lot of people are doing, and all the more power to them. That's, I think, the more conventional path, is to directly attack those questions. I'm suggesting a different path. And the different path is to take some inspiration from the classical to quantum transition and say that we don't have to try to wildly guess at the next step. We can prepare ourselves for where we have to go by talking about the physics we have right now in a way where space-time and quantum mechanics are not playing a starring role. Of course, it'll still be exactly local and unitary. We're not changing anything. But we're talking about it in such a different way that, in a sense, we're at least halfway there. We're learning how to talk about things that are precisely local and precisely unitary in a way where Hilbert spaces and space-time don't make an appearance. And hopefully, if we learn what that way of doing things is, in general, not just for this simple theory, but if we learn how to do it for any theory, then it will be like discovering the principle of least action. Then we can cogitate on that for a little while, and perhaps someone will have the inspiration to invent the path integral at that point. Okay, so that's why it's a two-step process. So it's a more indirect path to try to get to exactly the same questions. The disadvantage of taking a more indirect path is that you're not directly attacking those questions. The advantage is that you're on the straight and narrow path. I mean, you cannot mess around. You either get the 5-loop answer or you don't get the 5-loop answer, right? And if you don't, you know that you don't. So that, you know, you're on a very there are things that you're constantly being checked. On the other hand, you see, this is not a technical subject where you just have to work harder, you know, and it's not just, you know, you need some ideas. You need some ideas for what the principles are, what the picture might be, and we're very, very far from being done. I think this gives, to my mind, a first example that it's possible. I mean, I always felt that it was possible, but it was not obvious that it was possible. Even all the things that had been done through this point, you might just think, well, they're very clever ways of computing this, that, and the other, but ultimately it's standard quantum field theory which is behind all of it. And I think, at least to my mind, this really shows that that does not have to be the case. I mean, this is an object, as I said, I could describe to my to clever high school students, and they could discover that it has properties that some fancy graduate student recognizes as those of scattering amplitudes. I think the fact that that's possible, to my mind, just shows that this thing must be extendable, and it must be possible to describe normal physics in generalizations of this picture. But it could well be that what we're focusing on here for n equals 4 is a very special aspect of it. Yeah.
There's a question over there.
Here. I have two questions. One is a bit more technical.
Speak up.
So the question is, you here talked about the planar diagrams.
Yes.
Do you have some ideas how do you do non-planar diagrams?
Yes.
So that's the first question. And the second question is more conceptual. And that's here, although you are doing n equals 4 and there are no RG flows, do you have some ideas how do you to understand the RG flow?
Yes, so those are both, of course, very excellent questions. Let me say so. The thing about non-planar, this is part of the first thing here. There is so much you see, let me say a naive statement. A naive statement is, look, obviously all this stuff is happening for planar n equals 4 super Young mills. This theory is integrable. It's so special. None of this is going to generalize. None of it's going to generalize at all. So that's a reasonable attitude. Except for the fact that, for example, the integrability plays not a single role in this discussion. Not once. It's just something you observe at the end of the day. Look, you have this nice polyhedron, and its volume has this Yangian symmetry. But if you didn't observe it, makes no difference, right? It's not like because there are all these symmetries, you use the symmetries to solve the problem. It doesn't have that flavor at all. The symmetries are kind of an output. They're not playing a central role in the formulation. That's one thing. Another thing is that this general connection between on-shell processes and amplitudes goes beyond n equals 4 super Yang mills. And goes beyond integrability. The fact that with less supersymmetry, it's possible to represent amplitudes in this on-shell way. When it was n equals 4, all the combinatorics of how those on-shell diagrams are glued to each other ultimately comes from the amplituhedron. It's very hard for me to believe that, but with less supersymmetry, the same kinds of things are true. The same kind of combinatorial miracles have got to be true for it to be true. It's very hard for me to imagine that some extension of these things are not relevant for that, even with less supersymmetry. Then there's going beyond the planar limit. And here, again, there are lots of things that are opposite to what you'd expect. In many ways, amplitudes have more magic beyond the planar limit, not less. And there are even properties of the planar amplitudes themselves that are mysterious to a planar person and only make sense when you think of it as being embedded in the bigger non-planar structure. Okay? So, and there are these really remarkable things like these Bern-Carrasco-Johansson relations and so on that I think you heard about from Henrik's talk. So these things all have to, these are at the moment isolated things in idea space, but they're obviously got to be related to each other. So that says that there's even more beyond the planar limit and not less. To your second point is, I think your second question about the renormalization group is, to my mind, the deepest and most interesting question in this business. And let me go back to this picture. Okay. So indeed, n equals 4 does not have an RG. When we study when we study the connection between on-shell processes and scattering amplitudes with less supersymmetry, immediately, even with n equals 2, there is an RG flow. And what we found, and this is in the work back in December, where we showed how these things, how the Grassmannian structure generalizes beyond n equals 4, is that it's exactly the same structure in the Grassmannian, exactly the same positive Grassmannian. The only difference is that there's also a measure on this positive Grassmannian. In n equals 4, the measure has the property that it just has singularities in one space. It has singularities on the faces of this positive Grassmannian. When you have less supersymmetry, so there's an RG flow, the measure has a singularity in another place as well. So there's the positive Grassmannian, and there's this other locus in the Grassmannian as well. And all of the ultraviolet singularities are localized there. There's a remarkable geometric fact that place in the Grassmannian and the positive Grassmannian don't intersect each other. So that's the Grassmannian representation of UV-IR decoupling. Okay? But there it is. Clear as day, there is a second structure in the Grassmannian corresponding to ultraviolet divergences. Okay? And it needs to be studied. No one has studied it. But you notice this equation, right? That equation is the sort of fundamental invariant property of scattering amplitudes, right? That's what tells you the singularities of the object here. I mean, I've deliberately been vague about what that means. For this purpose, it means the singularities of this thing. I've also written it like boundary or like derivative, okay? In different cases, different meanings of that interpret this equation in different ways. But when you interpret it as singularities of, has these two pieces, then this clearly has to do with amplitudes. And you can think of the entire structure that I'm talking about as a way of making this fact obvious, which is not the conventional one, a different one. Okay? Now, of course, you'll recognize this equation from many, many places. It's a very famous structure all over the place in quantum field theory. But specifically related to your question, this is exactly the structure of the Wilsonian renormalization group equation as written by Polchinski. Okay? Totally different interpretation. You think of the blob as the effective action, and this is what happens as you integrate out a little slice. There are two things that can happen. You can have, a mode caught between the cutoff and a little lower cutoff, and you can just have a mode in a loop diagram caught between the cutoff and a slightly lower cutoff. Okay? So the fact that you have exactly the same kind of structure controlling the renormalization group as well as scattering amplitudes, coupled with the fact that we see these two different parts of the Grassmannian, one of which is infrared physics and one of which is ultraviolet physics, makes me hope that the structure that we're seeing glues in a nice way to something that makes that obvious. Okay? Now, the way as physicists we're used to making, the reason I think that your question is such a good one is because the Wilsonian renormalization group is the place where the usual way of doing field theory is at its absolute peak, right? Scattering amplitudes, you might think, it's very nice that there's a way of talking about amplitudes which doesn't involve local evolution, because scattering amplitude isn't a local question to begin with. However, the renormalization group is an incredibly local question to begin with. So, in a sense, the most challenging place to look for the idea of emergent spacetime along these lines is to try to understand the origin of the renormalization group without using Wilson. Okay? If we use Wilson, we know how to do it. But if the whole ideology is correct, there must be some way of thinking about it that doesn't use Wilson, some other structure that makes this emerge without using Wilson. Of course, Alan Kahn and Dirk Reimer and their friends for 15 years have been talking about this Hopf algebra structure that underlies the renormalization group. And there's a hope, I think, still very vague right now, that the structure they're seeing and the structure we're seeing with the amplitudes will smoothly glue to each other somehow. That's a very long-term thing, but to my mind, that's the most interesting question in this business.
Okay, one last question, and then we go to lunch.
So it may be very mundane, but how close are you to calculate quark-quark scattering where the quark interchange low momenta, meaning where they are in the non-perturbative regime with this scheme?
I mean, this is all in perturbation theory for n equals 4 super Yang mills. So very far.
Okay, let's thank Nima again.